बिस्मिल्लाहिर्रहमानिर्रहीम अस्सलाम वालेकुम। कैसे हैं आप? दिस इज लेक्चर नंबर 18। लेट्स स्टार्ट। So first we take a review of previous lecture. In last lecture we discussed how to describe a frequency distribution using 5 elements. Number 1, total number of observations in a data point. Number 2, the measure of central tendency such as mean, median, mode. And number 3, measure of dispersion such as variance, standard deviation. And next we discussed number 4, which is skewness, which measures lack of symmetry, whether distribution is equally spreaded around the mean value or it is unequally spreaded. And last one, the 5th one, we discussed the kurtosis, which measures the peakedness of the frequency curve. So using these 5 elements we can describe the basic features of any data sets. So we can, in other words, we can describe any frequency distribution using these 5 basic elements. And then in the last lecture we discussed the probability, and we introduced the probability, and we discussed some basic definitions related to set theory and basic concepts of probability. So objectives of the current lecture: in this lecture we are going to define the probability in a proper way, and we will also discuss its properties, and we will also discuss some of the basic questions related to probability. And then in the later half of this course, in this lecture we will discuss some laws of probability, and then we will also discuss some additional examples related to probability. So let's start. Okay, let us first define the probability. So probability of an event A. So let S be a sample space and A be an event in the sample space S. So then the probability of occurrence of event A is defined as probability of A, which is denoted by P of A. It is equal to number of sample points in A divided by total number of sample points. So note that symbolically we can write it as probability of A is equal to number of sample points in A. So NA is used to represent number of sample points in A divided by NS, which is number of sample points in sample space. So symbolically probability of A, P of A is equal to NA over NS. So now briefly we are going to discuss the properties of probability of an event. So probability of S, where S is the full sample space, it is always equal to 1. So, and number 2, for any event A, probability of A is lies between 0 and 1, where both 0 and 1 are included. So probability can be 0, probability can be 1, and it can also take any value between 0 and 1. So from this property we can see that probability of an event can never be negative, or it cannot exceed 1. So if A and B are mutually exclusive events, so note that A and B are mutually exclusive events, mean that we have an event A and an event B and their intersection is empty. So in case of mutually exclusive events, probability of A union B is equal to probability of A and plus probability of B. We will also explore this third property in greater detail when we will discuss some laws of probability in the later half of this lecture. So these are the 3 most common properties which are used. They are related with probability of any event. So let's proceed further. So let us discuss one simple example of probability. So example is a fair coin is tossed once. So we have tossed a coin one time. So find the probabilities of the following events. So first event is an head occurs, and second event is a tail occurs. So since here our main focus is coin tossing, so sample space in this case will contain two elements, the two possible outcomes, which are the head and the tail. So sample space is H and T. So total number of sample points, they are 2. First one is head, second one is tail, so NS is 2. So let us define an event A which represents the occurrence of head. So then this event A will contain only this entry H for head, and number of sample points in A are 1 in this case, only head, so NA is 1. So we want to find the probability of this event that head occurs. So it means we are interested in finding the probability of A. So according to definition of probability of an event A, it is equal to number of sample points in A divided by total number of sample points in the sample space S. So here, as far as this particular example is concerned, number of sample points in A are 1. There is only one sample point, which is head, and number of sample points in S is, they are 2, so head and tail. So according to this formula, we will write NA instead of NA 1, and divided by, instead of NS we will write 2. So 1 by 2 is the required probability, or probability of getting an head when a fair coin is tossed. So 1 by 2 is 0.5, or we can write in percentage form, which is 50%. So probability of head is 50%. So now we want to find the probability of occurrence of a tail when a fair coin is tossed. So again, let us define another event B which represents the occurrence of a tail. So the outcomes, this tail, so B event has only one outcome, which is T. So number of sample points in B is 1, which is tail only 1. So probability of B is number of sample points in B divided by number of sample points in S. So according to this formula, NB is 1 and NS is 2, so 1 by 2, which is 0.5, or it is also 50%. So when a fair coin is tossed, so probability of occurrence of head is 50%, and probability of occurrence of tail is also 50%. So we can say that since the coin is fair, so probability of head is same as probability of tail. So when a fair coin is tossed, so head has same chance of occurrence as tail has. So this is how to solve some basic problem related to probability. So let us discuss one more example. So in this example, a fair die is rolled once. So we are rolling a die. So find the probabilities of the following events. So in part A, the question is an even number occurs. In part B, a number greater than 4 occurs. In part C, a number greater than 6 occurs. So since here the question is about rolling a die, so sample points, the sample space will contain all possible outcomes when a die is rolled. So when a die is rolled, we know that die has 6 faces, so it means the total number of sample points are 6, and sample space will contain the number of all possible outcomes, which are 1, 2, 3, 4, 5, and this one 6. So total number of sample points in this case are 6. So NS is 6. So now come to this first part A. So it is asking us to find the probability when an even number occurs while rolling a die once. So part A is an even number occurs. So let us define an event A. So let A be an event which represents that an even number occurs when a fair die is rolled. So we can see that an even number mean from this sample space 2 is an even number, 4 is also an even number, and the third even number is 6. So it means A can take any of these three possible values. So 2, 4 and 6. And total number of sample points in this case is we have 2, 4 and 6. So there are 3 sample points. So number of sample points in A are 3 and A is 3. So according to probability formula, probability of A is equal to number of sample points in A, our total number of sample points, or number of sample points in S. So NA is 3, where NS is 6. So 3 over 6 is 1 by 2 or 0.5 or 50%. And part B says that a number greater than 4 occurs. So in order to find the probability that a number greater than 4 occurs when a fair die is rolled, so we have to define another event B. So let B be an event which shows a number greater than 4 occurs when a fair die is rolled. So number of possible outcomes of this event B are number greater than 4. So greater than 4 mean from your sample space look at the numbers which are greater than 4. So greater than 4 are number 5 and number 6. So it means these two are the number of possible outcomes of this event B. So we can say that number of sample points in event B are 2. So NB is equal to 2. So probability of event B is NB divided by NS. So number of sample points in B divided by number of sample points in S, which is sample space. So NB is 2, sample space has 6 points, so 2 over 6, it is 1.3, 1 over 3 or it is equal to 0.333 or 33.33%. So it means there is 33.33% chance or probability that when a fair die is rolled, a number greater than 4 will occur. So a number greater than 4 will occur. Its probability of occurrence is 33.33%. So now come to the last part, the third one, C part. A number greater than 6 occurs. So here is the C part, a number greater than 6 occurs. So let us define a third event C. So let C be an event which shows a number greater than 6 occurs. So look at this sample space. We can see from this sample space that the total number of possible outcomes are 6, which are 1, 2, 3, 4, 5 and 6. So from this sample space we can see that number greater than 6, there is no possibility of getting a number greater than 6 because a fair die has 6 faces. So there is no chance of getting a number greater than 6. So it means in this case the event C will be empty. So in other words, the total number of sample points in C, they are 0. So using the definition of probability, probability of event C is equal to number of sample points in C divided by total number of sample points in S. So 0 divided by 6, which is 0 or 0%. So we can say that there is 0% chance of getting a number greater than 6 when a fair die is rolled. There is one very important point to note here is that usually a die has 6 faces, but in some cases we can have a die having 8 faces. So in that case, in those questions, it will be properly specified in questions that an 8-sided die is rolled. So if it is not mentioned that how many faces a die has, so usually it is assumed that it is the usual die containing 6 sides or 6 faces, and the faces are 1, 2, 3, 4, 5, 6. So these are the numbers. But in some cases we can have a die having 8 faces or having more than 8 faces. So usually 6 and 8 faces are usually used. But if it is specified in question that the die is of 8 faces, then we will construct our sample space according to total number of possible outcomes in case of 8-sided fair die. So in that case the sample space will be 1, 2, 3 up to 8. But if it is not mentioned in the question, then we will assume that a die has the usual 6 faces, where each face represents a number from 1, 2, 3, 4 up to 6. So let us discuss another example of the probability. So if 2 fair dice are thrown, so 2 fair dice are thrown, so what is the probability of getting a double 6, and what is the probability of getting a sum of 11 or more dots? So these are the 2 parts which we have to solve in this example. So which indicates that which is related to 2 dice. So when 2 dice are thrown, what is the probability of getting a double 6? So here when 2 dice are thrown, so sample space contains these points, these 36 points. So 1, 1, 1, 1 mean on both die 1 occurs, and next 1, 2 mean on die 1 number 1 occurs, and on die 2 number 2 occurs. So when the both dice are rolled, so on die 1 1 occurs, on die 2 3 occurs, and next 1, 4, 1, 5, 1, 6, and next on die 1 2 occurs, die 2 1 occurs, and so on, 2, 6, 3, 1, 3, 2, 3, 6, and last one is 6 occurs on both die. So both dice has 6. So when we tossed both dice, so we get 6 on the first die as well as 6 on the second die. So counting all these possible outcomes, we can see that the total number of sample points are 36 in this case. So we can also get this number by 6 raised to power 2, which is 6 cross 6, and it is 36. So when 3 dice are rolled, so total number of sample points will be 6 raised to power 3, so which will be 6 cross 6 cross 6. So 6, 6, 36 into 6, 216. So similarly for 4 dice, the total number of points will be 6 raised to power 4. So this is the general formula in order to get the total number of sample points when any number of dice are rolled. So in case of n dice, so 6 raised to power n. If n is 1, 6 raised to power 1, it means there are total 6 possible outcomes. If n is 2, it means 2 dice are rolled, so total number of sample points will be 6 power 2, which is 36, and so on. So we can take different values instead of n in order to get sample points for different number of dice. So okay, coming back to this problem. So here our sample space has 36 possible outcomes. So question is, what is the probability of getting a double 6? So we will define an event A which represents that a double 6 occurs, which shows that double 6 occurs when 2 fair dice are rolled. So from this sample space we can see that this double 6 occurs only once in this case. So it means this is the possible outcome of this event A. So 6, 6, only one possible outcome in this case. So number of sample points in A, it is only 1. So probability of this event will be it is number of sample points in A divided by total number of sample points in S. So 1 divided by 36, we get 1/36. So 1/36 is the required probability. That probability of getting a double six is 1/36. So now the second part is the sum of 11 or more dots. So in order to answer this question, we need to define another event B. So let B is any other event which shows a sum of 11 or more dots occur. So sum of 11 or more dots. So from this sample space you have to check how many possible outcomes which is related to this event B. So we can see that, so in this case the 5 plus 6, the sum of these two dots is 11, and 6 and 5 again 11, and 6 plus 6 it is 12. So sum of 11 or more, so 11 or more, so from this dot you can see that here sum of these two is 1 plus 1 2. So it means this first order pair is not satisfying this condition, that sum should be 11 or it should be more. Similarly 1 2 or 2 1 2 2 1 3. So here 4 5 3 6 9 5 4 9 6 plus 3 9 6 plus 4 10 5 plus 5 10 6 plus 4 10. So all the numbers, most of the numbers in this sample space, their sum is less than 11. So only these are the three possible outcomes. So 5 plus 6, the sum is 11, and 6 plus 5, the sum is 11, and last one is 6 plus 6, the sum is 12. So these are the three possible outcomes of this event B. So that's why these have been put here. So B is equal to 5 6 6 5 and 6 6. So total number of sample points in B are 3. So 1 2 and 3. So probability of B is NB over NS. So NB is 3 divided by number of sample points. Total number of sample points, they are 36. So 3/36, or you can simplify it. So 3/12. So 1/12. So this is the required result. So this is how you can solve simple probability questions. So here we have another example. So a fair coin is tossed 3 times. So a coin is tossed 3 times. So what is the probability that at least one head appears? And next, what is the probability that more heads than tails appear? And third one is exactly 2 tails appears. 2 tails appear. So since the coin is tossed 3 times, so our sample space will contain head on first, head on second, and head on third. So we have to write the number of all possible outcomes when 3 coins are tossed. So head on all 3 coins, then head on first 2, tail on third, then head tail head, head on first, tail on second, and head on third, then tail head head, head tail tail, tail head tail, tail tail tail, and tail on all the 3 coins. So now if we count all these 1 2 3 4 5 6 7 8, so total number of sample points in this case is 8. And remember that a coin has 2 faces. So in this case 3 coins are tossed, so 2 raised to power 3. So 2 raised to power 3 means 2 into 2 into 2, so 2 to the 4 to the 8. So when a coin is tossed 2 times, so we will use this formula 2 raised to power 2, which is 2 cross 2, it is 2. When it is tossed 1 time, so 2 raised to power 1 is 2. So general formula for finding the total number of sample points when a coin is tossed n number of times, it is 2 raised to power n. If n is 2, so we will write 2 raised to power 2, which is gives us 4. So when n is 1, so we get 2 raised to power 1, which is 2. And when n is 3, 2 raised to power 3, we get 8. So similarly when 4 coins are tossed, so it means 2 raised to power 4. So this n is replaced with 4. So this is 2 into 2, so we have to multiply 2 4 times. So 2 to the 4, 4 to the 8, 8 to the 16. So total number of sample points when 4 coins are tossed, they will be 16. And similarly you can calculate the total number of sample points when a coin is tossed any number of times. So here, as far as this particular example is concerned, the coin is tossed 3 times. So total number of sample points in this case are 8, where head occurs on all 3 coins, and then head and tail, and next head tail head, next tail head head, and last one is tails on all 3 coins. So now part A is at least one head appears. So let us define an event A. So let A be an event which represents that at least one head appears when 3 coins are tossed. When one coin is tossed 3 times or 3 coins are tossed once. So this is around the same. So you have a coin, you tossed it 3 times, or you have 3 coins, you toss them once. So both experiments are the same. So here a fair coin is tossed 3 times. This means that one coin is tossed 3 times, or we can write it alternatively as 3 coins are tossed once. So these two statements are the same. So at least one head appears. So let us define an event A which represents that at least one head appears when a coin is tossed 3 times. So at least one head mean one head appears or more than one head appears. So it means we have to consider here as far as this outcome is concerned, one head appears, and here one head appears and 2 are the tails, one head appears, 2 are the tails. And next we have to consider also the possibility of 2 heads, because our question is at least one head. At least mean one or more than one. So this will be also included, this will be included, this will be included. So last one is 3 heads, so which is also satisfying this condition that at least one head appears. So it means we have to consider all these possibilities in this case. So this event A will have these outcomes. So these 7 outcomes. So number of sample points in A are, just count these are 7 in number. So NA is 7. So in order to calculate probability of an event A, it is NA over NS. So NA is 7 and number of sample points in S are 8. So N over 8, this is 7 over 8. So this is the required probability of getting at least one head when a coin is tossed 3 times. So let us move to the next part. So next part is more heads than tails appear. So let us define another event B which represents that more heads occur than tails. So more heads mean the number of heads should be more than the number of tails. So here you can see that as far as this first element, first outcome of this S is concerned, there are 3 heads and 0 tails. So it means heads are occurring more than the number of tails. Here in the second case, there are 2 heads and only 1 tail. So it means this second option, it is also satisfying this condition that more heads than the tails. And here we have 2 heads and 1 tail, 2 heads, 1 tail. And here we have only 1 head but there are 2 tails. So it means this condition is not being satisfied in this case. So we will not consider this one. So we have to consider only these first 4 outcomes. Why? Because if we look at this one, so here again there is only 1 head, 2 tails, 2 tails, 1 head, and all 3 tails. So as far as our event is concerned, it is more heads than tails. So we have to consider only the first 4. So just write them here. So total number of sample points in B, they are 4. So probability of B is NB over NS. So NB is 4, where NS is 8. So 4 by 8 is 1 by 2, 0.5 or 50%. So probability of getting more heads than tails is 50%. So now move to the third part, C. Exactly 2 tails appears. So 2 tails appear. So let us define another event C, which represents that exactly 2 tails appear. So 2 tails appear here. Focus on the first outcome in this S. So we can see that all 3 heads are they have appeared. So it means this is not satisfying this condition that exactly 2 tails appear. So move to the next. Here again we have 1 tail, so this is also not satisfying the condition 1 tail, 1 tail. So we have to discard first 4. And look at this next entry, the 5th one. So here we have exactly 2 tails. Although we have the third one head, but 2 tails mean we are this condition is being satisfied. So we will write this number here, HTT, and then here again we have 2 tails, THT, and here again we have 2 tails, 1 head. So so these are the 3 numbers, 3 outcomes which are satisfying this condition. So total number of sample points in C, in this case they are 3. So probability of C is NC over NS. NC is 3, NS is 8, so 3 by 8. So let us consider another example. So an employer wishes to hire 3 people from a group of 15 applicants. So these applicants include 8 men and 3 women, all of whom are equally qualified to fill the position. So if he selects the 3 person at random, so what is the probability that all 3 will be men? So from this question we can see that there are total 50 applicants, including 8 men and 3 women, and they are equally qualified. So it means we can select either males. Men have they have the same chance of being selected as the women have. So question is, if he selects 3 person at random, so out of these 15, 3 are selected. So at random mean they are selected in such a way that chances of selection of all the individuals, they are same. So what is the probability that all 3 will be men? So here, since we have total 15 applicants, we have to select 3. So from 15 we have to select 3. So it means in order to select 3 persons, we have to take the rule of combination. Why we are using this rule? Because selecting 3 people from the 15, since the order doesn't matter here, so we can use the combination rule which we have studied in our previous lecture. And if we have to select these 3 individuals out of 15 by following a certain order, then in that case we can use the permutation rule. But here, since we have to select 3 persons at random out of 15, so we can use the combination rule. So in order to find here total number of sample points, we will use this rule. So total number of ways in which 3 people can be selected out of 15, this is given by 15C3. So 15C3, we know that NCR, this is also written as NCR. So its formula is n factorial over r factorial into n minus r whole factorial. So as far as this particular problem is concerned, we want to calculate 15C3. So it means instead of n, we have 15 factorial, 3 factorial, 15 minus 3 whole factorial. So this is 15 factorial, 3 factorial, 15 minus 3 is 12 factorial. So we can write it as 15 into 14 into 13 into 12, 11, so on. So 12, 11, 10, 9. So I have written 12 factorial to represent all these numbers. So here we have 3 factorial, which is 3 into 2 into 1, and we have this 12 factorial as well. So cancel this 12 factorial with 12 factorial. So we are left with 15 into 14 into 13 in the numerator, and in denominator we have 3 into 2 into 1. So just simplify these two expressions. So 3, 5, 15 and 2, 7, the 14. So now multiply this 5, 7 and 13. So 5 multiply with 7 multiply with 13. So 13 into 7 is 91. So it means 5 cross 91. So 5 into 91 is 5 in 1 the 5, 5, 9, 45. So we get total number of sample points. In this case they are 455. So we can also use calculator to find this NCR or 15C3, and we can also use Microsoft Excel to calculate this 15C3 as well. So let us calculate this 15C3 in Microsoft Excel first before proceeding further. So suppose we are interested in calculating this 15C3. So this can be calculated by using combine command. So you can see from this Excel tooltip that it is asking us that this combine returns the number of combinations for a given number of items. So here just put the parenthesis, and then it is asking us to provide the number. So for the number just type 15 and then comma. The second argument is number chosen, so comma 3. So this will calculate, this will give us 15C3. So combine 15 comma 3, press enter. So result is 455, which we have calculated using this formula. So if you want to calculate 15C3, so just type combine 15 comma 3 and press enter. So it is 455. Or suppose if you are interested in calculating 3C0, so in order to calculate 3C0, just write combine, and then first argument is the number 3, then comma number chosen is 0, press enter. So we get 1. So 3C0 is 1. So similarly 3C1 can be calculated as combine 3C1, so it is 3. So similarly you can calculate this choosing any numbers from a total of any outcome using this combine command. So let us move back to the main question. So let us discuss another example. So 6 white balls and 4 black balls, which are indistinguishable apart from their color, they are placed in a bag. So in a bag we have 6 white balls and 4 black balls. So this is important. So if 6 balls are taken out from the bag, so it means 6 are selected. So find the probability of getting 3 white and 3 black balls out of these 6 selected balls. So probability of getting 3 white and 3 balls. So here the total number of possible equally likely outcomes are, so since we have 6 white and 4 black balls, so 6 plus 4 a total of 10 balls in this case. So total 10 balls. So out of 10 we have selected 6 balls. So we can select these 6 balls. They can be selected out of 10, and these 6 can be any of these 10 balls. So we have total 10 balls in the bag. So out of these 10s, any 6 can be selected. So question is how to select, or what is the required, in how many ways we can select 6 balls out of 10 balls. So actually there are a large number of ways in which we can select 6 balls out of a total of 10 balls, because the balls can be first 6 or 1, 2, 3 up to 5 and 7th ball, 1, 2, 3 up to 5 and the 8th one, and 1, 2, 3 the first 5 and the 9th one, and first 5 and the 10th one. Or the balls can be 1 skipping the second ball, so 1, 2, 3, 4, 5, 6, 7, or 1 skipping the second, 1, 3, 4, 5, 6 and 8th one. So similarly, once you are finished with this option 1, you can skip this first ball and you can start with selecting second, third, fourth, fifth, sixth, 7th ball, or the next possibility can be second ball, third, fourth, fifth, sixth, skipping the 7th, 8th, then second to 6, the 9th ball, second to 6, and then the 10th ball, then start with 3. So you can see that there are a number of possible ways in which we can select 6 balls out of 10. So how to calculate the total number of possible outcomes? So we can use the rule of combinations. So total number of sample points in this case, they can be easily found by using this rule of combination, so which is 10C6. So 10C6, so it can be calculated by using this formula NCR, which can also be written in this way, NCR. So it is n factorial over r factorial n minus r whole factorial. So as far as our case is concerned, we have 6C10, so it will be 10 factorial over 6 factorial 10 minus 6 whole factorial, or further simplifying it, 10 factorial 6 factorial, and this 10 minus 6 we have 4 factorial, or further this is 10 into 9 into 8 into 7 into 6 into 5 4 3 4 3 2 1. So 6 5 3 2 1 we can write it as 6 factorial. So here we have 6 factorial and this 4 factorial, I am writing this 4 factorial as 4 3 2 1. So you can see that this 6 factorial is cancelled with 6 factorial, then this 4 into 2, this is 8, this is cancelled with this 8, and next we can cancel 3 the 9. So you can see that 10 into 3 into 7, so this is the simplified form of this expression 10C6. So 10 3 30, so 30 into 7 we get 210, so which is our required result. So we can also calculate this combination using Microsoft Excel or using simple calculator. So let us first move to the Microsoft Excel and we'll demonstrate how we can calculate this combination. There is one simple built-in function in Excel which can be used in order to calculate this 10C6 or NCR. So let us move to the MS Excel. So suppose we want to find 10C6. So in order to calculate it, there is one built-in function which is combine. So you can see from this Excel tooltip that it is asking us that this command returns the number of combinations for a given number of items. So how many possible combinations can be obtained? So first is the number. So here we will write 10 and after comma the second option is number chosen. So we have to select 6 out of 10. So the number chosen is 6. That's it. Press enter. You will get 10C6. So it is same to 10, which we have calculated using the simple formula. So similarly you can calculate any combinations. So 3C2 for example. So for this the command is combine and then 3 and the number selected is 2. So 3C2 it is 3, or similarly you can select 4C2 suppose. So 4C2. So in order to calculate it, so combine 4 comma 2, press enter, so 4C2 is 6. So this is how we can use this built-in combine function in order to calculate this combination, so 4C2. So let us move to the our main question in the PowerPoint slide. Okay, here total number of sample points when 6 balls are selected out of 10, they are 210. So our question is, find the probability of getting 3 white and 3 black balls. So let us define an event A which represents that 3 white and 3 black balls are occurred. So number of sample points in A will be calculated as, so look at here, so there are 6 white balls and 4 black balls. So just write 6 and 4, the total number of 6, total number of white balls and total number of black balls. And now question is, we want to select 3 white, so these 3 white, they will be selected from the white balls. So since there are 6 white balls, so we will write here 3, so 6C3, it means 3 white balls, they have been selected out of 6 white balls. And similarly we have to select 3 black balls, so these 3 will be selected from a total of 4 black balls which are available. So out of 4 we have to select 3 black balls. So this is how to find the total number of sample points. So then we have to multiply this total 6C3, yani in how many ways 3 white balls they are selected out of a total of 6 white, and in how many ways 3 black balls are selected out of 4 black balls. So once we have this number in hand and second one in hand, then we will use the multiplication rule to get the total number of sample points of this event A. So 6C3 multiplied with 4C3, you can calculate 6C3 using the Excel and 4C3 as well, or using simple calculator, or you can even calculate these numbers by using this formula using simple algebra. So this is, the result is 80. So NA, number of sample points in this event A, are 80. So now we want to find probability of A, which is NA over NS. 6C3, 4C3, or 6 and 4, they are total 10, and this 3 and 3 total 6, or 10C6, which is 210. So 80 over 210, the 0 is cancelled with 0, 8 over 20. So this is the required probability of getting 3 white and 3 black balls when 6 balls are drawn out of a total of 10 balls which are available in a bag, and these 10 balls are containing 6 white and 4 black balls. So now we discuss some laws of probability. So if A is an impossible event, so then probability of A, it will be 0. So for any impossible event A, the probability will be 0. So 0 means it has 0% chance of occurrence, or there is no chance of occurrence of this event A, so it means A is impossible event. So next is, if A complement A dash, this A dash is also used for complement, or usually A and we write C in the superscript. C stands for complement, or usually dash is used. So A dash is complement of an event A, so relative to sample space S. So then probability of A complement will be 1 minus probability of A. So here in the Venn diagram we have this rectangle which is showing the total sample space S, and here we have an event A. So, and other than this event A, this white portion in this box, this is called A complement. This full portion, this white portion, this full portion, this is called A complement. And remember that the definition of A complement is S minus A. So just subtract A from total S. So from this case you can see that since this A and A complement, they are disjoint. Disjoint means there is nothing common between event A and event A complement. So probability of this A complement will be total probability, which is 1, and 1 minus this probability of A. Or actually if you take probability of left hand side as well as probability of right hand side, so probability of left hand side A complement and probability of right side S minus A. So here we have simple rule that probability of first and probability of second. So note that this probability of S is 1. So this is 1 minus probability of A. So it means probability of A complement is 1 minus probability of A. So probability of A complement is 1 minus A, or you can, from this result you can switch the role of A and A complement. So just shift, interchange their position. So shift this probability of A from left hand side to right hand side. So its sign is negative here, from right hand side to left hand side. So currently it is on right hand side with negative sign. So when it is shifted to left hand side, it will become positive. So we are left with 1, and here we have probability of A complement with positive sign. When it is shifted to right hand side, it will become minus. So this is another rule. So probability of A is 1 minus probability of A complement, and probability of A complement is 1 minus probability of A. So next, addition laws. So law of additions. So if A and B are any two events defined in a sample space S, so then the probability of their union, A union B, so it is equal to probability of A plus probability of B minus probability of A intersection B. So let us look at this Venn diagram. So here we have event A, event B. So suppose we want to find the probability of A union B. So A union B is this full portion, this shaded region. This is showing us the A union B. So probability of this full shaded portion, or A union B, this is equal to probability of A. So probability of A means we have to consider this full area, this one. Probability of A means this full area A. So then we have to add to it the probability of B. So then this again full area of B. So but currently you can see that this middle area, it is being counted twice. Once in case of probability of A, so this area is counted, this middle area, and second in case of probability of B. So since this is counted twice, so that's why we have to subtract it from this sum. So this middle area is the common portion of A and B, which is A intersection B. So it means we have to subtract it once from this sum. So probability of A union B is probability of A plus probability of B minus probability of their intersection, that is A intersection B. So there is one corollary or simple result which have been derived from this main result is, if A and B are two mutually exclusive events. Two mutually exclusive events mean there is nothing common, that their intersection is empty, it is phi, empty set. So if A and B are two mutually exclusive events defined in a sample space S, so then probability of A union B, this is equal to probability of A plus probability of B. So here you can see that in this Venn diagram the intersection of A and B is empty. So you can write this empty set in this way or in this way. So there is nothing common in both events A and B. So it will be this first event, the probability of A, and then we have to write this second event, which is probability of B. So now since there is nothing common between the two, so there is no need to subtract this quantity which is A intersection B, because A intersection B is 0 or empty set in this case. So this is another formula. If they are mutually exclusive, then probability of A union B is probability of A plus probability of B, and if they are not mutually exclusive or there is something common, so then the probability of A union B is probability of A plus probability of B minus probability of A intersection B. So if we have three events, if A, B, C are any three events defined in a sample space S, so then probability of A union B union C, so then probability of A union B union C, it is defined as probability of A plus probability of B plus probability of C minus A intersection B minus B intersection C minus C intersection A and plus A intersection B intersection C. So here is the Venn diagram. So when we write this probability of A, it means we have covered this full set A. So note that this full set A, it is also contains this middle portion which is common both in A and B. Similarly, it also contains this middle portion which is common in both A and C. So when we write probability of A, it means it is this full area A, and then probability of B, it means this full area B. So look at here, it means this we have counted this middle portion which is common to both A and B twice. So we have to subtract it here. And similarly, when we add this probability of C as well, so it means we have to subtract this common portion which is common in both B and C as well as common to A and C. So that's why this A, B and C and A, this intersection of probability of B intersection C is subtracted as well as probability of C intersection A is subtracted. And as far as this middle portion is concerned, this one, so you can see that this middle portion, it is common to all three. So when we write here probability of A, it means we have counted this portion. Similarly, when we write here probability of B, we have again counted this portion. So this portion is counted twice. Then probability of C, so this part is also occurring in C, so we have counted it thrice. So when we subtracted this A intersection B, so this part, when this full part is subtracted, it means this was subtracted once. When we subtracted this A intersection C, so this part is again subtracted. So when we subtracted this B intersection C, so this middle part, it was added three times when we write probability A, B and C, and when we subtracted these three portions, so it is subtracted again three times. So it means up till here, up till this term, we have added these all portions, but this middle portion, it was added three times and it was subtracted three times. So it means we have not counted this middle portion yet, and this middle portion, it is what? It is the intersection of A, B and C. So that's why we have to add this middle portion which is A intersection B and intersection C. So this is how we can extend the addition law of two events to three events A, B and C. Similarly, this law can be generalized to 4 events, 5 events, or in general we can say that we can generalize it to n events. So similarly, if A, B and C are 3 mutually exclusive events defined in a sample space S, then probability of A union B union C, it is probability of A plus B plus C. So we can also express this result using Venn diagram. So it is event A, event B and event C. So you can see that there is nothing common in these three events, or we can say that their intersection is empty. So in this case, A intersection B intersection C, it is empty, and also there is nothing common between A and B, nothing common between A and C, nothing common between B and C. So in this case, probability of A union B union C, it is the sum of their individual probabilities. So these are called the addition laws. So now let us discuss the structure of a deck of playing cards. In most of the statistics and probability, there are several questions which are related to the cards. So it is better to have the full idea of a deck of playing cards. So here in this slide, I have put the full details related to the cards. So total cards in an ordinary deck, they are 52, and there are 4 suits. First suit is spades, second is heart, third is diamond, fourth one is club, and there are 13 cards in each of these suits. So, and face value of these 13 cards in each suit is they are ace. Ace stands for 1, and then 2, 3, 4, 5, 6 up to 10. So these are 10 cards, and next 11th one is called jack. Usually J is used to represent jack, and then 12th one is queen, Q is used, and last one is king, where K is used. So here in this picture we have the cards. So this is the first one, is the first row of the cards, they are the club cards. So you can see that we have the ace. So A is usually used to denote ace, then number 2, 3, 4, 5, 6, 7, 8, 9, 10, and next jack, queen and king. So these are the 13 cards. So in next suit we have spade, the same 13 cards, 1, 2, 3 up to 10. So instead of 1 we have an ace card, and next last 3 are the jack, queen and king. And next we have the hearts, and last one is diamond. So you can see that we have 13 cards in the first suit, 13 in the second, 13 in the third, and 13 in the fourth. So 13 plus 13 plus 13 plus 13. So it is 13 plus 13 plus 13 plus 13, which is total of 52 cards. So another point to note that are that the club cards and the spades, they are black in color. So it means there are total of 13 plus 13, 26 cards are black, whereas the hearts and diamond cards, they are red in color. So it means 13 and 13, so 26 cards are red in color. So this is the basic structure of and a deck of ordinary playing cards. So now we will cover certain questions which are related to these cards, and remember that you have to keep in mind the total the structure of these cards in order to answer these questions. So there are certain more points. You can see that there is 1 king in each of these suits, so total of 4 kings. So 1 king in each of these suits, similarly 1 queen in each of these suits, and 1 jack, similarly 1 10 in each of these suits. So for each type we have 4 numbers, 4 aces, 4 twos, 4 threes, 4 kings, 4 jacks, 4 queens. So now we have a special names as well. So honor cards are the ace card, the 10, jack, queen and king. So these cards are called the honor cards. And the face cards are those cards on which we have different faces. So you can see that we have pictures or faces on jack, queen and king. So these three are called the face cards. And there are certain games of cards. So some of the most popular games are the bridge game and the poker game. So now we are going to cover some related questions which are related to the cards. So example is, if a card is drawn from an ordinary deck of playing cards, find the probability that it is a red card, or find the probability that it is a diamond card, or it is a 10 card, or the card is a king or a face card. So first, the total number of playing cards are 52. So our sample space is 52 in this case. So NS, total number of sample points, they are 52, and sample space is the set of all 52 cards. So number of sample points, they are 52. So now coming to the part A, a red card. So what is the probability of getting a red card? So define an event A, let A be an event which represents that a red card is drawn from a deck of ordinary playing cards. So you can see that, you know that there are total 13 are the hearts and 13 are the diamonds. So diamonds and hearts, they constitute the red cards. So it means there are 26 cards which are red and the remaining 26 are black cards. So number of sample points in A are 26. So probability of A is 26 over 52, or it is 1 over 2. Now the card is a diamond. So define an event B. So let B be an event that card is a diamond. So you can see that there are 4 suits. So one of the suits is diamond containing 13 cards. So if the chosen card is a diamond, so it means it can be any of these 13 cards. It can be ace of diamond, the 2 of diamond, 3 of diamond, 4, 5, 6, 7, 8, 9, 10th of diamond, jack, queen, king. So it can be any of these 13 diamond cards. So it means number of possible outcomes or NB, number of sample points of this event B, they are 13. So probability of B is 13 over 52, or 13 for the 52, it is 1 by 4. So third part is, what is the probability that card is a 10 card? So let us define another event C which represents that the drawn card is a 10. So note that there are 10 occurs in each of the 4 suits. So 10 occurs in club, 10 occurs in spade, 10 occurs in hearts, 10 occurs in diamond. So it means the total number of sample points in C are 4. So probability of C is NC over NS, so 4 over 52. So you can cancel it, 4 1 the 4, 4 13 the 52. So it is 1 by 13. So next card is a king. So define an event D. So let D be an event which represents that the drawn card is a king card. Again, out of these 54 cards, we know that in each of the suits we have one king. So king in spade, king in club, king in heart, king in diamond. So there are 4 kings. So it means the total number of sample points in this event D, they are 4. So probability of D is 4 over 52, which is 1 over 13. And next we have to find the probability that the selected card is a face card. So we can see that face card mean on which there are faces, or we have pictures. Picture card is also called face card. So there are 3 cards in each of the suits which are face card, and these are the jack, queen and king. So 3 cards in first suit, 3 in the second, 3 in the third, and 3 in the fourth. So if we define an event E which represents that a face card is drawn, so the total number of sample points in E will be 12, which is 3 in the first suit, 3 in the second, 3 in the third, and 3 in the fourth. So Jack, King, Queen, these are the 3 face cards. So in 4 suits, so we have 3 plus 3 plus 3 plus 3, which equals 12. So probability of E is equal to 12 over 52, or you can cancel it with 4, 4 3 the 12, 4 13 the 52. So 3 over 13 is the probability of getting a face card out of 52 playing cards. So this is how you can solve simple probability questions. So the only thing you need to know is the structure of a deck of playing cards. So once you know the structure of playing cards, then you can answer any of the questions which are related to the probability. So let us review the main concepts which we have covered in today's lecture. So in today's lecture we have defined the probability in a proper way, and then we discussed its properties, that probability, it lies between 0 and 1. Probability can be 0, it can be 1, it can never be negative, it cannot exceed 1. So, and probability of total sample space S is 1. And then we discussed some basic questions related to the probability, and then we have discussed some laws of probability, and then further questions related to the deck of ordinary playing cards. So in the next lecture we will study conditional probability, and before studying the conditional probability we will cover some more examples of probability, and then we will discuss conditional probability, and then we will discuss independent and dependent events, and we will also cover their related examples. So till then, Allah Hafiz.